All right, so exponential decay. This is the second part of 10.6. Now, exponential decay is using the same formula that we've been used to. So our y equals c times 1 plus r to the t power. This time, our rate is just going to be negative. So if they say there is a decrease, if it's decay of some substance, things like that, what we're going to do is just make the rate of change negative. So let's example. So since the rate is negative, we can think of a general question as subtraction. So our new formula, instead of having addition, we're just going to have subtraction. So I wrote out an example for you. It says if you buy a plasma TV for $1,000 and its value decreases at a rate of 23%. So again, that word decreases means that we're going to have that subtraction symbol in our formula. At the rate of 23%, the equation would be, so here you've got 1 plus a negative 0.23, always changing your percent into a decimal, and then just raising it to that t power again. So that way the t represents the amount of years. You can also just write it as subtraction in your parentheses. Okay, so first example. This is in 1950, the use of coal by residential and commercial users was 114.6 million tons. Many businesses now use cleaner sources of energy. As a result, the use of coal has decreased 6.6% per year. So again, decrease means I'm using that formula with a subtraction symbol in the parentheses. So now I'm just going to replace my C and R with the appropriate numbers. So I'm looking for C as my initial amount. So that's going to be that 114.6. My percentage, that 6.6%, I'm going to make that into a decimal, and always remembering to move over the decimal place twice. Now I'm going to write 1 minus that decimal and raising it to the t power. So now our next part is we're going to take and figure out what the amount of coal would be used in 2015. And this would be interesting to see if this model actually works, to look up online to see how much coal we even use this year. So in this case, the time is going to be the difference between 1950 and 2050. That's 65 years. So I'm going to put 65 right here. And then from here, I'm going to subtract inside the parentheses, raise it to that power, and then multiply by 114.6. So once you pause the video, figure out what that answer is going to be, and then we'll check and verify it next time I see you. Now we have to look at whether or not a exponential equation is growth or decay. So the way to do this is if you have a number that is in between the parentheses that is greater than 1, then it's going to be growth. If it's less than 1, then it's decay. So let's take a look at these 4 examples. The first one is growth. The second one, I see 0.82, which is decay because it's less than 1. Number 3 is decay, and 4 is going to be growth again. So we should be able to just look at it and say, okay, that's going to be a growth exponential model. That's going to be decay, just by seeing the equation. All right. These are just some more examples of your growth and decay, just like the ones that we just looked at. And just realize that to get the number that's inside the parentheses, you're just subtracting that percentage, that interest, that decimal that you found from 1. That concludes this video, and we'll discuss that answer from the previous example.